no ar.
Well, thank you for the people that are here and people that are online for this workshop. This second workshop for the Metroclima project is for us to present what we have been doing since now, some results that we already have, and also the sites that are online measuring. I will only present some motivation, because after my presentation we are going to have the presentation of the results, and then what I'm going to do is only to start discussing some motivation for the project. This data, it's very recent data that's from this greenhouse gas bulletin from the WMO, and it shows the concentrations of CO2 and also the growth rate of CO2 since 85. And what we can see is the increase in the concentrations, and also here is the comparison from 22 to 7050, the usual before the industrial area. And we have here the amount of the increase in the concentrations, and also comparison for 1 year, from 2019 to 2020, the increase in concentrations in ppm, ppb for CH4 and ppb for NO2 and 2O, and also the increase for this greenhouse gases, considering here 10 years of data. This shows that there is a problem, that is the increase of these greenhouse gas. They are important for the global changes. And another aspect relevant is that we have only a very few data. We can see that at some places we have more data. Here it's the places that are operational, that are working, and some only partially and not reported data, for instance. And what we notice here that always we have a few data, and mainly in the South Hemisphere and mainly here in the South America. Then we notice that it's important to increase the number of stations. And what we have also is that most of the data is data that is from remote areas. Sorry, from remote areas. No. Since some years, there is a concern about the emissions by the cities, and why the cities are important for the emissions of the greenhouse gases. Because what we have is that for energy and for the transport sector, usually for considering energy as a main source, we have the cities. Sorry, it's not you. We have the cities and the energy they use as emissions. People are migrating for the cities. That we are going to have less people in remote areas going to. In Brazil, especially in Brazil, we have 85% of the population in urban areas, and now these emitting a lot of greenhouse gases. And we have very few data, not only here in Brazil or in the South America, but also in now the world, with measurements in the cities. And when this is also very recent data, when we look to the emissions, we note that we have here total greenhouse emissions in the world. We have many cities with high amount of emissions related to the big cities. And also when we note that the Asian cities have the worst configuration. But anyway, we have these high contributions from the cities to the emissions of the greenhouse gas. I know that here is not possible to see in details, but when we observe the main sources, we have the transport sector that's in the blue, the energy sector, and also industrial process, and also in the cities, the main sources are industrial and also the waste disposal and industrial emissions and transport sector. When we go to remote areas, we have the burning and the biomass burning, also forests burning, and also this other process related to forests deforestation. This is from the Brazilian emissions inventory for greenhouse gas. We can note here that the main sources for the urban area in the state of São Paulo are related to energy, very different from the north of Brazil, that's related to the change of deforestation, basically deforestation, and cattle and animals. And when you go to the cities, to the municipalities, the first one that in total emissions of CO2 is this region that's related to the deforestation. The three biggest emissions of greenhouse gas are related to deforestation and change of the soil related to plantations and also cattle and all these sources. São Paulo is the first one and is related to the industrial and energy and mainly transportation sector. But we know that the urban emissions, because the estimation of the greenhouse gas emissions is based on we have this emissions factor, and then we have the emissions factor, and then we consider the total amount of, for instance, when we have the vehicular emissions, we have the total amount of vehicles, and then we multiply by the emissions factor, and then we multiply by the kilometers per day that the cars run. And then what we have is an estimative that can have a lot of uncertainties. And it's difficult to implement policies for controlling the emissions when we don't know exactly how much is these emissions. The only way is to have the monitoring of the emissions. And when we go to the São Paulo state, we can find the data for São Paulo, Paulínia, other cities, and we see that São Paulo is the main one, that's the transport sector, but the Paulínia, Cubatão, and São José dos Campos are related to the industrial emissions. We have the total estimative of the emissions, but we know that there are many problems with these total emissions if we compare with our measurements data. We have also in São Paulo, we had some projects, and until now we have projects also more related to the aerosols characterization. For instance, the Nuance project that finished some years ago. But we keep in this new Metroclima project, we keep also the aerosols because they are also related to the radiative process. And then the Metroclima project is related to the greenhouse gas and also to the aerosols and the radiative properties of the aerosols in São Paulo. We are focusing in the São Paulo area. And in the project, we propose to have measurements and also modeling. And in the measurements, we propose to have surface and also flux and satellite, all this data. And in the modeling, we already had some atmospheric modeling of the aerosols and pollutants, and trying to include now the whole of the greenhouse gas that's going to be shown by all the participants. The goals proposed was then to have a discrimination of the GHG and the pollutants and the aerosols, and the impact of the emissions from the area of São Paulo, and also the impact of the climate change to the concentration of the pollutants in São Paulo. We divided the project in main tasks, and the results that are going to be shown are related to this. That's the first was the implementation of the network, development of emissions inventory, development of the atmospheric transport modeling for the greenhouse gas, and assesses the impact of climate change feedback on the air quality of the metropolitan area of São Paulo. This was the main activities, and the results that are going to be shown are related to these activities. Some key science questions that were proposed in the submission of the project, and are very difficult, I must say. That's to estimate the anthropogenic urban carbon flux of São Paulo, and if it's possible to simulate the carbon flux associated to biogenic fluxes. And also we have this bottom-up emission inventory, if it's possible to reconcile with the top-down. That's not easy. Improve the emissions in space and time, and how these emissions can be related to different urban environments, thinking about geography, topography, climate, and the ecosystem type. The framework of the project was thinking about these main questions, is to have the emissions inventory, to have the modeling, including the modeling for the greenhouse gas, combine this with data, also satellite data, FTIR, LiDAR, and ceilometer, observations, and having this at the end, the conciliation between the modeling and the measurements at the surface. If we consider the diagrams of the activities, we have separate for particles with measurements in situ and remote sensing, and also in the gas phase, considering the pollutants, regulated pollutants, and also all the data related to the greenhouse gas. The experiments that are being performed is we have these 4 sites with data from surface data for CO2, CH4. That's going to be detailed next in the next presentation. Also 1 site with flux for CO2 in the park, in the Cientech Park, and also the FTIR, that all these are going to be presented next. And tomorrow, the presentations will be concerned with the regulated pollutants, and we are going to have these emissions factors that were calculated for vehicular and also other kind of sources like cooking and gas, charcoal and wood, and also the measurements of particles with some data for mass and number size distributions. Only to illustrate, here we have the 4 sites that with the Picarro system for measurement of the greenhouse gas, and 1 site that's in the Cientech Park in the south of the city, that's with flux measurement with irrigation system. In the modeling that also will be going to be present today, there is this inclusion of the description of the emissions by the vegetation. We have the metropolitan area, different kind of vegetations that are in the southeast and in the north, mainly in the southeast and in the northeast, and also in the urban area, some parks that have impact on the balance of the greenhouse gases of the CO2. Well, we have also put some expected results and also some innovation that's related to the emissions inventory, to the use of experimental results to check these emissions for the greenhouse gases. also starts the measurements and validations of the fluxes of the greenhouse gas, the incorporation of the inverse modeling, that's also going to be presented, and try to evaluation the contribution of the MASP region to the emissions, and at the end, with the modeling, evaluate the climate change scenarios and also this impact of these scenarios on the air quality in the southeast region of Brazil. With this, it's only an introduction, and the program for today is that we are going to have the presentation by Daniel Castelo, that's CO2 Background estimative. Daniel Castelo is a master student. Then we are going to have the presentation of the network, the greenhouse gas network, and will be done collaboration with Noele Francisco, Carlos Oliveira, Agostinho Medeiros. I think Carlos is going to present. He is a postdoc. The data related to the FTIR will be presented by Diogo Medeiros, that is a postdoc, and Professor Marcia Akemi. We are going to have the modeling with WRF-VPM by Rafaela Alves, a PhD student, and Professor Rita Ynoue. And then we are going to have the satellite retrieval data with Izabel Andrade and Professor Eduardo Landulfo. Izabel Andrade is a doctorate student. And we are going to have the questions in the end of the presentations. Then I would like to ask Daniel to do his presentation.
Okay, thank you. I will share the screen. Hello, everybody. Everybody is seeing my screen?
Yes.
Sim.
Okay, thank you. So my name is Daniel Prado Castelo, and today I will present a part of my master research, and the theme is the estimation of background concentration of CO2 in São Paulo City. This work was supervised by Professora Maria de Fátima, and so let's start. To start this presentation, I will answer some of the questions of background. And so I will try to explain what is the background definition and how can we interpret the background in the urban city, because we are studying in São Paulo City. So a definition of background by European Environment Agency is background concentration is the concentration of a substance in an environment medium, air, water, or soil, that occur naturally or is not the result of human activity. So here we have first, the two important words. The first one is a natural concentration, and the second one is we don't have a human activity to when you are estimating the background. A second definition is by Giostra, 2011. A general definition of background mixing rate of a given species is the mixing rate in a given air when the recent contribution of local source is absent. So here, the word local source is very important, because when you try to estimate or calculate the background, the local source is a problem to this estimation. So, but when you talk about city, you know city has a human activity and you have a local source. So the question is, how can we avoid this local source, or how can we not compute the human activity to achieve estimation of background in the city? So to answer this question, the shell 2010 say the classification of the air quality monitoring station is a complex issue. There is always the question if the urban background station is directly influenced by the local emission source and if it's representative to characterize the background level. In other words, you have uh, to look for the local emission and to answer this question: how can we not compute the local emission? It's a big problem, and how can we use a station as a urban background station? And Verhulsten, 2017, answered this question, saying, estimate greenhouse gas at local scale require measurement that resolve variability. So the big problem here is the variability. How can we achieve a low variability to get a good estimation of background? So I will try to answer these questions during the presentation, but just to give a context of this project, uh, in São Paulo, we have five stations, and we have chosen the Pico do Jaraguá like a urban background station. And the four main reasons for this, the four main reasons is the Pico do Jaraguá is the furthest station for the urban area. Pico do Jaraguá is inside a state park with native vegetation. Between between the five stations, Pico do Jaraguá has the highest altitude. It's very important to atmospheric mixing, and Pico do Jaraguá has the longest measurement history. It's another very important point. So to avoid the influence of local emission or human activity, you have several methods in the literature. And here I give some examples like statistical filter, meteorological filter, chemical filter, spectral filter, and backward trajectory. And this presentation, I will pick one, the statistical filter, and try to explain and use an example to achieve a background estimation for the city of São Paulo. So the statistical filter is based in the variability data to estimate the background concentration. This method is very simple to be used because you just need the data of the measurement. So if you have the CO2 data, you can estimate, you can use this filter. So it's a very positive point of this method. So basically, we will use a statistical parameter to achieve a low variability of the data. And because when you have a low variability, we are closer to the mixed atmosphere. And a mixed atmosphere is favorable to a condition to background estimation. So you will try this approach to estimate a background. So this work is inspired in Verhulsten 2017, and Verhulsten used three criteria to achieve the background estimation. The first one is a small degree of variability within 1 hour period. Two, small hour-to-hour variability. And the third one, the persistence of the first two conditional for several hours. In other words, and you have to understand how can we eliminate the data that that have a big variability to and in this example we have tried a lot of iteration and we achieved these three parameters. For the first criteria, you use the maximum standard deviation of 1.25 ppm. For the second one, so we have for the first criteria, in 1 hour, you look for all the points, all the data you have in 1 hour, you look for a standard deviation. If this standard deviation is bigger than 1.25, we eliminate this hour. The second criteria, we look for the max variability hour to hour. So we will look if in the second hour, the variability is bigger than 1.25, So we eliminate the data. If the variability is small, then 1.25, okay, just the data passed through the second criteria. And the third one is the percentage of the first two criteria for 3 hours. So you need to have the 3 hours consecutive to achieve the third criteria. So after applying these three criteria, you have this graph. The black dot is the point. In fact, it's all the measurements. So you have outliers, you have a big variability of the data. But when you apply the criteria for these points, you have the red dots, is the select data. So the red dots is the dots that are passed by the filter. So we call the points of backgrounds. And the blue dot is the smooth curve. So we apply CCGCRV technique. It's a technique developed by Tuning in 1989, and it's used to smooth the curve. You have a representative curve for the CO2 gas. So here you can see the curve. The blue curve is a stable curve. You don't have a lot of variability. So it's a very good indicator of background, and you can see the curve is increasing over the years. Another way to look at the data is if you calculate the average value by the year. So here you have in orange the average value by the measured concentration. And when I say measured concentration, is the all data. And in blue, you have the background concentration. So we can see for the station Pico do Jaraguá that the measured concentration has increased 2.5 ppm by year, and the background concentration has increased 2.8 ppm by year. If you look for the same period, 2019, 2021, you look for the global carbon dioxide growth rate, you achieve 2.5 ppm a year. So the results is very close, and it's very important result. Another way to look is about the CO2 excess in this station. So if you have the measurement less the CO2 background concentration, you have approximately exact concentration of the city. And this value here is more or less 4 ppm. Another way to look at the data is if you look for it by month. So you can see the curve over the month. So again, the orange curve is the measured concentration with all data, and the blue curve is the background concentration. So here is very interesting to look that the small difference between these two curves is in the first month of lockdown to the COVID. So here we have the curve is very closer, and in fact the 3 months, April, May, and June, that was the month of the most intense lockdown, you have the small difference of these two curves. And finally, another way to look at the data is if you look for the hours of the day. In other words, you can group by the data by hours of the work, and you can estimate the excess of concentration. And this graph show this period between 10 to 14 o'clock. You have a small difference between the measured and the background concentration. And we have some points here. Between this period, you have a strong influence of photosynthesis vegetation, and you have a mixed atmosphere with a convective mixed layer. And between 19 or 7 p.m. to 18 a.m., we have a big difference, like 5, 6, 7 ppm. And this different, this excess value is big, is very big, and we can say in this period we don't have a photosynthesis, we don't have the photosynthesis of vegetation, and we have a stable boundary layer. So without the sun, we don't have photosynthesis, and we have a stable boundary layer. So these two big difference can influence in the results of the human contribution. And so I would like to thank you everybody and pass to the next one.
Thank you, Daniel. Now I invite in the sequence, Dr. Carlos Oliveira to do his presentation.
Hello, good afternoon, everyone. I will make a thank you, Fatima, for. I will talk briefly about some improvements of GHG measurements, surface measurements in the network, regarding specifically of the data processing strategies, quality control, and checks, calibrations, and about network compatibility in order to, with a specific objective, to see the assure the comparability of the results for different stations. As a summary, this is, as Fatima previous talked, is the GHG network with the surface measurements of CO2, CH4, and CO in one station, carbon isotopes as well, Flux in others. Here, Pico do Jaraguá, we have CO2, CH4 measurements. It's the highest places of measurements with a well-preserved region. Here, IAG, it's a suburban area. Here we have measurements of CO2, CH4, and carbon isotopes. In the UNICID, the highest urban and traffic area influence, which will measure CH4, CO2, and CO, carbon monoxide. Here in SASP, in the top of the building, we measure flux measurements. And here another vegetated area, which will measure flux, CO2 flux mainly. Here we have a ceilometer as well to measure PBL rates. This is a summary of the strategy to process our data in the all the stations. We have manually and automatic data collections in some stations by API in the smog server. After this, we, together with Logbook, we filter using PyCRDS developed by the Marcia and which work with the team in the first 2 years to assess the data and to create averages, hourly, minutes, and daily averages. And this data is available as well in the web platform in dashboard. This is the dashboard we assess we check the accuracy and the quality of the data, which will be measure every time. This dashboard is updated by a day, automatically, or by a day, by a week in some stations. Now we are, Noele, the technician people, is working specifically as well with logbook registrations, and a new approach of the automatically logbook registrations of the maintenance mistakes in the data and the other things, in order calibration as well, in order to flag the data to help in the processing of the data. Here the example of the flag 1 day of calibration data. For example, here another day of calibration data. So in this context, I'll talk about our strategy to calibrate and check data accuracy and the reproducibility and other things. We use it in all the stations calibration tank, Ynoue WMO scale is certified in this scale, and another target tank as well with certified values, but we use the target tank as an unknown sample in order to check our instrument stability and to check the calibration strategy as well, to calculate the accuracy and precision of our measurements. Currently, we have 3 standards in the Ynoue scale as well, certified, which you can apply linear fit for CO2 calibrations. Another approach, very interesting, is important as well to correct our data. And a third approach is we have made the comparability between the instruments of the stations in order to assure that these instruments measuring the same standard and the same air samples could have the minimal difference between the measurements in order to make possible the comparison of the concentrations measured in each stations. And it's named by WMO as network compatibility. Okay, two checks is important, which we measure is repeatability and reproducibility of the data in short and long term. This is an example of the measurement of the same standard, Ynoue standard, in the same days. And with this approach, the standard stay measured by about 20 minutes. We can calculate the mean and the standard deviation. The standard deviation is our repeatability, the standard in each room. And the deviations for all this sequence is our reproducibility by a day. However, it's very interesting for us to see the repeatability in each days and all the reproducibility for long term, for months, for a year, for example. And you can see that is very stable. It's very precise, the measurements of these standards over days, over months. And our reproducibility is about around 2.12 ppm. it's very precise for this kind of measurement. Another strategy is regarding, for instance, calibration strategies. In the first of our measurements, when we didn't have three tanks with different concentrations, we needed to adopt single point calibrations with target tank in calibration tank. In this strategy, you use sensitivity, or it's a slope between the calibration, the measured value and the certified value, which you use to correct the air data. For this approach, it's very interesting, very important that slope is not ever variable. Here, this is in the 40 decimal place. It's a good approach to. It's very stable as well. And current that I have said, we are performed as well in 3, 4, 6 months linear fit with standards with 3 different concentrations. We have the equation to correct this data as well. Comparing 2 different strategies, we have similar accuracies. It's good as well for approach to compare data. To perform these curves, we measure for 4 cycles, the 3 standards and target standard as well to perform our linear fit. This is international by ICOs, WMO advice. And the other way to check the compatibility of our data is to measuring. We put the instruments of different stations. We pick up the instruments to IAG, and we put the same instrument, the 2 instruments to measure the same air samples for 3, 4, 6 days a week, and the same standards as well. It's very important to see if the instruments is measuring the same thing. It's the part of this graph. It's part of exercise to compatibility. It's very interesting that the difference between the instruments is about 1 ppm. It's the measure. The measure uncertainty of our network, I think something about 2, but the main part is about 1 ppm. It's very precise we compare data of these different stations. For example, here we have the comparison of annual means of the years 2020, 2020-21 for IAG, for Unicid, and for Pico do Jaraguá. And we see these 3 stations have different characters, which is very impressive. This characters seems be represented by CO2 diurnal cycles of these stations, which our background candidate have the lower means, hourly means, And the IAG stations at night have the higher CO2 values, and the high traffic Unicid station have the characteristic rush hour peak. To finish, it's other means seasonal means distributions for two stations. We see that for IAG and Unicid, we have the minor difference between the seasons, and the most difference is observed in the Pico do Jaraguá stations, maybe more controlled by PBL height and vegetation as well. It's the previous preliminary conclusions about these graphs. Okay, I thank you again for the opportunity to show some improvements of the network.
Thank you, Carlos. Thank you for the presentation. Now I'd like to invite Dr. Diogo Medeiros, that we are going to present the results related to FTIR.
Thank you, Professor Maria de Fatima. Let me just load my presentation in a second. So yeah, for those of you who don't know me, I'm Diogo Medeiros, and I'm a postdoc here at the University of São Paulo. I work under the supervision of Professor Marcia, whose comments and corrections are always much appreciated. And yeah, I appreciate the presence of all of you in the meeting today. So today I'm going to be presenting some of the results we've got while looking into the atmospheric columns of greenhouse gases in the metropolitan area of São Paulo. It's an ongoing work. The results need some refinement, so I would ask you to take the results with a pinch of salt, but things look promising, you see. So yeah, in this presentation, I'll show you a site description, so just some information about the metropolitan area of São Paulo, the plan of work that justifies the work that we've done so far. The presentation will be actually focused on the progress. I'll show you some preliminary results, and I'll also discuss some points to be done in the future. So it's been discussed by others already, so I will be quick. But if anyone is not very familiar with the geography of Brazil, we're here in the red circle in the southeast of Brazil, in São Paulo. If we zoom in here, we'll see that the metropolitan area of São Paulo is consisted of 39 cities. And this region is very important for Brazil's GDP. So economically speaking, it's a very important region of Brazil. We're looking in the red circle. And if you want to see a quick picture from Google Maps, the red marker in the center shows where the measurement site is. On the northeast of this graph, of this picture, you can see. Yeah, I think it's. Let me try. Hello. Oh yeah, I think this one's better. Okay, so in the northeast of this picture, you can see a important highway next to a river. This highway it has a very intense traffic, and it provides good access to the southern regions of São Paulo. But this picture is just to give you a few of the sites where the instrument is installed. It's a majoritarily urban site. So just a few more facts about the metropolitan area of São Paulo. It has a total area of approximately 8,000 square kilometers, more than 20 million inhabitants, a total fleet of approximately 7 million vehicles. And São Paulo, the state of São Paulo, is responsible for about 30% of Brazil's GDP. And the metropolitan area of São Paulo is responsible for 85% of that. So it gives you about 25% of Brazil's GDP in one area. That's how important the metropolitan area of São Paulo is for our country. So yeah, let's go to the plan of work that justify what was done. So the idea here is that we want a plan that enables us to generate an infrastructure that will allow for daily measurements of greenhouse gases, of atmospheric columns of greenhouse gases. We not only want to collect data on a daily basis, we also want to analyze the data and hopefully compare that data with satellite data. If we can do that on a daily basis, we should be in good shape to then do even further work and very interesting comparisons and analyze stuff like environmental events, important environmental events that may occur. So this plan is focused on getting this objective done, but obviously we can do way more than just comparing data with satellites. Now, for those of you who are not very familiar with the instrument that we're using, that's the infrared spectrometer that we use. It's an instrument that is measuring the sunlight to then derive the concentration of the atmospheric columns of greenhouse gases. But it's very fragile. There you can see the mirrors that reflect the sunlight inside the instrument. It has a very thin layer, a coating layer of gold, and we can never touch these mirrors. It cannot get any water on them, so we have to work really hard to make sure we're not touching the mirrors. So it's an instrument that's usually, it needs to be outside to make measurements of the sunlight, but it's fragile, so we can't leave it unattended. That's why in our plan we have as a first thing the construction of an automated housing for it. So if you want to collect data on a daily basis effectively, you will need something like that. In order to derive the atmospheric columns from the spectra collected by that instrument, because what it gives you is a spectra, right? It's spectrum. But then you have to derive the atmospheric columns from the spectra. For that, you need measurements of pressure, atmospheric pressure as well. We have developed a control box that not only controls the opening and closing of the shelter that we have constructed, but it also collects pressure. And that allows us to derive the atmospheric columns. So following the plan, we then install the M27 inside the housing. I'll show you some pictures of the housing. And we've been working into coding to, on a daily basis, collect data without human interaction, analyze the data without human interaction as well, run the statistics, and also do the comparisons with data from satellite. For now, we're using Tropomy data only, but having the code working for Tropomy should make it easier for other satellites as well. So the progress. This is what we idealized initially. It's a housing, it's a sliding housing. So the idea is that the instrument is inside it, and whenever we want to make measurements, the housing will slide on top of rails. The rails are not represented in the picture, but then it will reveal the instrument to the sun. And then when the conditions are not appropriate, or if there's no more sun, then the housing will shut. We can control this manually if we want to, but the idea is that the computer will make the decision of opening and closing this. This is what we ended up getting. The shape is slightly different, but it works perfectly. This was installed in August last year, but then we spent some time developing the control box for it and the coding to make sure we are doing things with safety, making sure that the instrument is quite expensive. So we don't want this to get stuck or to fail when deciding if it should be open or not. And this is a picture of the instrument installed inside the housing. It's on top of the Palletron building. So the instrument was installed on the 3rd. We spent like 4 months testing the housing before installing the instrument. And there was no event of rain when the housing was open. So the control box is working reliably. It always decides to close the shelter when it realizes there's too many clouds in the sky, or if there's no luminosity enough, it will close the housing. This is what the control box looks like. It's an Arduino-based solution. It has a bunch of sensors inside, and it has a 5 volts relay that activates the electric engine that opens the housing. The sensors on top are the luminosity sensor, the round one. The one with the soft drink cap is an infrared sensor that detects the presence of clouds in the sky. The square thing here with the stripes is a rain sensor, but the rain sensor is just the last resort. We don't want to rely on the rain sensor. The idea is we make the decision based on the other sensor to predict if it's going to rain, but the rain sensor is there just as an extra safety feature. So the preliminary results that we've got by using this, this is the diurnal cycle for CO2. As I said, there was not much refinement done. This is generated automatically by the analysis. But this is just to give you a feel of what we can do with this instrument. It's quite powerful. We can have a look at the dry air mole fractions of greenhouse gases on a daily basis. And these are the averages for the diurnal cycles. So this is the data for CO2. I brought you an example for data for methane as well, and some data for carbon monoxide. These are all data for the month of April 2022. And finally, the last piece of code that we've been working on was the comparison with Tropomy data. So the only blue dot right there was calculated for an overpass on that day, the 24th of April. And as you can see, there's a very good agreement for the Tropomy measurement of methane compared to what we've got. The uncertainty on the Tropomy measurement was taken from an average of all the points within a radius of 100 kilometers for methane from our site of measurement. We've done the same for carbon monoxide, but we used a shorter radius. We used 50 kilometers. These numbers were taken from a recipe in that paper right there. I was honestly focused on getting the infrastructure, the coding up and running. And once we're happy with it, then we can easily just adjust these parameters and reanalyze the data. But as you can see, I think we're off to a good start. This is a summary of all the measurements that we've got. So the algorithm that I've programmed is downloading the Tropomy data on a daily basis and working out if there are points with good quality. So I'm only using Tropomy measurements with the highest quality possible, so 100% quality. I noticed by just quickly looking into the data that the points that do not agree the most are the ones where you don't have uncertainties in the Tropomy measurement, like the second one, for example. And that happens when you don't have that many pixels with the highest quality. So, but this is something that needs refinement. As I said, it's just a first attempt, but I would say it already looks very good. And the same for the dry air mole fractions of CO. Is a good agreement. As you can see, these data here were the last data were generated last week. Okay, so in terms of future work, we want to run more tests that improve the control of the analysis algorithms. We want to refine the statistical analysis of the results and do some cross-analysis with surface measurements. Carlos has been working on that, and I'm surely going to talk to him about these. We want to refine the comparisons with Tropomy. As I said, they are preliminary results. They're already looking good, but definitely we can do a better job. And we want to incorporate code to automatically compare with GoSat CO2 data, which is also available. I'm not doing any comparison at the moment. But having the Python scripts running for Tropomy should make it simpler to adapt things for GoSat. Stuff like calculating overpasses and things should be straightforward from now. Yeah, so I would like to thank you for your presence again.
Thank you, Diogo. Very nice presentation. Then I'd like to invite Rafaela Alves, that's going to make her presentation. Thank you, Rafaela.
Hello. 1 minute. Okay. Hello, my name is Rafaela Alves. I am a PhD candidate at University of São Paulo, and my advisor is Rita Ynoue. And my project is entitled CO2 Emission and Dispersion Modeling at Metropolitan Area of São Paulo. My contribution to Metroclima project is related to the topic atmosphere modeling. And I will start this slide. And this graphic shows energy sector is a measure to contribute to CO2 emissions in the state of São Paulo. that related to burn fossil fuels, fugitive emission, and transport sector. This other graphic in right refers to the city of São Paulo. The only sector of emissions is in the transport sector and divide two sources, burn fossil fuel and fugitive emissions. And these informations are from official report for São Paulo. The main objective of my project are simulated biogenic and anthropogenic emissions and dispersion with the WRF-VPM model. Evaluate model results based on field measurements within the Metroclima project. Compare the contributions of biogenic and anthropogenic source of CO2 in the MESP. MESP is a metropolitan area of São Paulo. And study the impacts of different emission scenarios on CO2 concentrations in the MESP. This flowchart is a summary of the principal steps of my methodology. First, to simulate emissions of the source anthropogenic and biogenic. For biogenic emissions, you use the Vprm model. For anthropogenic emissions, you performed tests with two different vehicular models that were developed for the metropolitan area of São Paulo. The Venn model and the Lapat model. And finally, we performed CO2 simulations with WRF-VPM. Now I will start to talk about biogenic emissions with Vprm. And I performed some tests and used Vprm offline in Python code, which was based on Medeiros' article. The Vprm model considering climate data, vegetation indices, and parameters that are source of flux tower data. And the temperature and radiation are used of WRF model. But Brazil doesn't have works with the Vprm model, and the flux tower data are very difficult to find in the southeast region. So I didn't have parameters for my study area, and when I did this test, but I used Medeiros' article parameters to validate the function of the Vprm model and to continue my tests while I find this data for my region. In my test, I used the product Caloid Mapa Biomas with a spatial resolution of 500 meters. It has 7 soil classes, and I considered the urban and water classes without CO2 flux. And the other vegetation classes have used the parameters of the Medeiros vegetation classes, as we can see by these colors. For example, in red, I used Harvard parameters for Atlantic forest. In this slide, I present the test we did with Vprm for the month of August 2020. The figure 1 represents early mean in that region. In red is represent metropolitan region of São Paulo. And what we can observe is that even with inadequate parameters for this study region, but Vprm can quantify CO2 flux for areas with vegetation when they are represented by good vegetation indices and the product of vegetation classification. Yeah, I didn't have flux tower CO2 data available to compare and analyze and optimize parameters, but not yet. But this test was necessary for verification and to perform another test with WRF-GHG. At the time, this was important for the implementation of the Vprm model, because we did not find anyone in Brazil who had already used this model. And I used these results for the WRF-GHG. In this slide that shows us the comparison with tower flux data by Freitas' study in Wright, and he did plotting the average daily CO2 flux for the dry and wet seasons, and I did the plot in left in the same area in the Freitas graph, because this area stays around the metropolitan region, and this area has a much vegetation. Our name is Serra do Mar, and we can see that both graphs are very similar in the intensity of CO2 fluxes, and the daily cycle same. But these results need very corrections, such as these parameters, and in these next steps. These figures represent CO2 emissions with the Vprm model, where only vegetation contributes. This figure 4 represents at 0 UTC. We can see only positive flux, and 12 UTC, we already have negative flux around the metropolitan region. Now I present preliminary results of anthropogenic emissions. I did 2 tests with 2 different vehicular models, the LAPAT model developed by Andrade and collaborators, and then developed by Ibarra. Both models were developed for the metropolitan area, but with different methodologies. In summary, the LAPAT CO2 emissions are high when compared to the VIN model and compare the official reports. The VIN model showed low emission, but I use a correction factor for emissions to be more similar to the official reports. For both vehicular models, the distribution is very similar. The measured emissions are in the central region in the metropolitan area of São Paulo. But the next step will be to perform the study and analyze this emission and correct for more real emissions. This slide shows the compare regional vehicular models, VAN and LAPAT, with CO2 global emissions from Edgar. The figure 6 represents CO2 emissions for the metropolitan area, only vehicular source, and we can see these emissions very low. They compare other vehicular models. But when I consider the other sectors, such as the energy sector, refineries, and industries, the CO2 emissions from Edgar are increased, and with values closer to the VIN model. The figure on the right represents the CO2 emissions of the global model ODAIC, and I was also used as the test in the simulation with the WRF-GHG for compare it to other models. Now I present preliminary results with the files of biogenic and anthropogenic emissions with together. These figures represent the CO2 emissions with the vehicular of the LAPAT model with the Vprm model, and the CO2 emissions of the VIN model with Vprm model. And we can see that the emissions from LAPAT and Vprm are much higher than the VAN and Vprm model, and this will be will be reflected in the simulations with the WRF-GHG that are yet to be shown. Now I present preliminary results about the simulated test with WRF-GHG. This graphic represents the simulated concentrations performed with the WRF-GHG for EAG site, but this simulation represents only with the anthropogenic emissions of the different models. The concentrations simulated with the Lapache and Venn models were the closest to the observed data concentration for this point. And remember that these are tests and the emissions and simulations will still be better evaluated and studied. And with the files of biogenic and anthropogenic emissions showed before, I performed the test with WRF-GHG model, but the intention is to make the model GHG run with emissions. So, an evaluation of the physical parameterizations of the WRF model has not yet been performed. And we did two simulations, one vehicular emissions by Lapache model with CO2 flux by Vprm, and the other vehicular emissions by Venn model with CO2 flux by Vprm. And next, we plot on the graph the two simulations of CO2 concentrations for each site. In red, only the vehicular emissions. In black, the simulation with Vprm and vehicular. And in purple, the observatory data. But you can see that the concentrations are very different from the observatory data, principal to intensity. But the perfil if Venn model and Vprm were very similar compared observatory data. My next steps, I will get local parameters for our study area, realize statistical optimization, and run new tests for CO2 flux with Vprm model, improve vehicular emissions with Venn and Lapache model, evaluate the WRF parameterization, such as the planetary boundary layer, and improve wind simulations, and run the WRF-GHG and compare CO2 simulated concentrations with observed data. Thank you, and this is my email, and if I can answer any questions or talk more about my preliminary results, I am happy to be able to answer.
Obrigada, Rafaela. Thank you, Rafaela. Very nice presentation. Thank you. Now I'd like to invite Professor Eduardo Landulfo, that's going to make his presentation, and also I think Amanda is going to present data related to the boundary layer measured at CNTech station. Eduardo?
Sorry, yeah, okay, the mic was off, okay. Can you see my screen? That's the question of the past 2 years. Can you see it?
Yes, yes, perfect.
Is it big enough? Okay. Let me see if I have a laser pointer here. Yeah, I do. Okay. So today we'll be talking about the approach that Metroclima is taking regarding the satellite retrieval. This work we have been doing that together with my PhD student Izabel and other students. And anyway, just regarding the greenhouse gases that mainly focus on carbon dioxide and methane, even though there are others that we can even retrieve from satellites.
Eduardo is not in the presentation mode.
Yeah, you should. That's the problem. I'll put, let me see if I can put it always that way. Let me see if I can put it the full screen.
Yes.
I always don't like it, but anyway. Yeah. What about now?
Yes.
Okay.
Perfect.
Does it change? Yeah.
Yes.
Okay, sorry. Anyway, so as I was saying, that there are other missions that can retrieve the other greenhouse gases, like ozone, for example, that was firstly the main gas that was the first retrieved by satellites, but we've been focusing on carbon dioxide and methane as the big guys, the bad guys, as we used to say. From the past presentation, we see that there are many factors, several factors, even when considering modeling or even when doing measurements, that not only has to do with, well, let's say, macroeconomics, the way the city works. And so that's always a challenge to see the best way to retrieve that. And as Fatima mentioned before, one of the key components is the satellite retrieval. And let's say one of the largest or the biggest challenge is to reconcile that with other observations. What you see sometimes with the satellite, it has to be somehow be the same or has to do with what you see in the ground. And so that's also a big challenge to do that. So the objective then would be looking at the methane, CO2 as well, but methane became very important as you see in the past. And they're using the Sentinel-5P, Tropomies, beside other missions that I'll mention to you. And we are using we are capturing down spectroscopy in the FTIR. So those are the systems that somehow we'll have to make the measurements, in a sense, make them not agree, but to speak the same language in the same units and things like that. And that should be covered over the metropolitan region of São Paulo. As you see, well, everybody knows pretty well, but it's a large area, and you have the city, like the dog face, the dog shape, as we always like to see it, and other 38 municipalities around it. And you have a diversity also of geography aspects, vegetation, and things like that. Fatima mentioned that the main source, according to the inventories, could be energy production, but we know that the vehicle fleet that's over 7 million plays a large contribution as well. And when you're considering that, it's always good to know how to separate, and also from the aspect from the satellite, if that's possible. So the missions that we are focusing on our study, it's Sentinel-5P, GO-SAT, which is the oldest one, released in 2009, OCO2 in 2014, even though that we have not long time ago, it's OCO3 as well, but we rely more on this data. And then we have here the spatial resolution that you see that they are very nice compared to the past missions like OMI, for example. And of course, we have also a visiting time that for Sentinel is daily, GO-SAT every 3 days, and OCO is 16 days. So in one key aspect that we always like to mention also is the swath. That would be the coverage that every overpass does. You can see here on the right that when you have this kind of measurements, Sentinel-5P has by far the largest swath. It's good because you're not only looking at one specific area, but a large portion, for example, of the Brazilian continent, for example. And here you have like globally what you can do. So for start, we should follow the methodology by Zhang and collaborators that I'll show. And then we started identifying the tropospheric density for source identification, average every 3 months. And then get a priority source of inventory data, mainly Edgar and SEG. And then one thing that Izabel is developing and dedicating a lot of time is start developing tools for larger data retrieval, and also getting this in a production in a batch way, because it's very time consuming if you do it one by one, for example. So as I mentioned, that the work by Zhang, it's quantifying methane emissions from the Permian Basin. For those that don't know, it's a place where one of the largest, if not the largest, production of methane and oil production in the US. So, and then what they did, were trying to more or less do the same idea and they follow the same script, so to speak, defining our area of interest. And then, as I said, we focus on tropomies like they did. And as a site measurements, they use VIRS, flare, ID. But that case for them because there are a lot of flaring there. That's not our case, but we can do that with NO2, for example, as I will show, which would be ancillary measurements. So that gives you an idea of the source apportionment. And then, based on observation, you have to do the prior estimates using Bayesian inversion that you can look at in the paper, the details, which has to do with the nested, sorry, let me see if I can, oops, I cannot hide, let me see. Okay, sorry. Okay, did you get back? Okay. So we have like nested geoscan transport model, and using as prior estimates the inventories and ground-based observations. They did that, for example, for bottom-up, and also the measure that they did. So that's the step they were following, more or less. So here, to give you a grip, like the Tropomies observation year 2019. So over the South America, it was produced by Henk Estes, our collaborator at ESA. And it's clear the patch that you see from the largest cities in the continent, like São Paulo, Rio, Buenos Aires, Santiago, and actually we just got a paper on that recently. So, and then we run the tropospheric condensed average for every 3 months and look at the seasonal response over the area. And then you can see that the seasonal pattern, how it follows from summer, autumn, and then winter and spring. And more or less, we try to keep it in the same units and the same scale. So that would be so, and then as the models, it's good to see here that, of course, the city has a lot of production, but it has to do with NO2, and also the area near Cubatão, which would be the industrial area of the metropolitan area, connected to the metropolitan area. So, and then we get the bottom-up approach from Edgar and from SEG, and then we compare the emissions based on those two bottom-up approaches. It's good to see that SEG, it's good because it has municipality by municipality, as Edgar is more like overall estimation. The same applies for CO2, and then that would be the the start for inventories. And then when you start getting Tropomy data, for example, from December 2018 to November 19, here you see the overall, and also if you see patches, you'll see clear areas because it has to do with the filtering. So perhaps you have to decrease the filtering. That will be a flagging, so telling to be less stringent when you decide to put or not, but more or less it covers the whole metropolitan area. When you decrease the time, then you see summer because it could be very related cloudy, the autumn, winter, spring. Spring seems to be the best time for these overpasses, but it's still working on that. So the next step, then that is the big challenge, then it would be like find an analytical solution for the Bayesian optimal estimate. And we got in touch with the group from Harvard University, which now they provide an integrated methane inversion. They would provide the grading for South America, and then we have that for São Paulo as well. They will be able to make the simulation. They do the simulation, then we extract the simulation for Tropomy column average dry air mixing ratio, and they run in the cloud based in Harvard the GeoScan 3D model that you can just get retrieve the results and then you have just for those that really understand that, but it's the average kernel vector, the dry mixing ratios, and the power estimate that from the bottom up and then that will be a big help for us. And of course, it will increase the speed that you can get results pretty fast. So it's the group from Geno Jacob and the group that now they're doing 12-based facility. They developed that, and we're happy that we just found that, and they're providing that. We have a close now connection. They're doing that right now in producing those. The other step is also based on the observations by Tropomy when they consider the wind speed and also the concentration. And then from that overpasses over all of the year, for example, they can extract what we call hotspots. One of them is not far from here. It's a landfill in the metropolitan area that they already were able to identify. And then we should get, and that's actually, we're planning to do that, from the other mission, that's GHG SAT, that's only devoted to methane retrieval, but with a much better resolution. For example, then they can get the emission exactly from the observation, so that would be also a big plus for us. So the tools that we've been using, Python, GitHub, now IMI from Harvard, and HARP, which is a tool from ESA, to get all this running in the hard work from Izabel and other colleagues. Okay, this is the reference, and thank you very much.
Thank you, Eduardo. Thank you very much. We have now the presentation by Amanda. We had this change in the program. Sorry for not including before, but is Amanda?
Hello?
Okay, presenting. Thank you.
Can you hear me?
Yes, perfect.
Yeah, can you see my screen?
Yes.
All right. Good afternoon. I'm a master's student at IPEN. My advisor is Dr. Eduardo Landulfo. And my project is on obtaining the planetary boundary layer top height over São Paulo with LiDAR and ceilometer data. So the main goal of my project is to use a LiDAR system and a ceilometer to detect the planetary boundary layer height over São Paulo using the wavelet covariance transfer method, and to compare the results of these two instruments, and also to carry out carry out studies on air quality and the transport and dispersions of pollutant and gases such as CO2, CO, and CH4, since the thickness of the PBL is associated with the dispersion of these pollutants and gases. So the planetary boundary layer is important to know to be able to study in a city such as São Paulo, since it has a large population and industrial presence, and to understand the impact of pollutant emissions, it is necessary to understand the processes involved in their dispersion. So the atmosphere extends up to hundreds of kilometers in height, but the lower layer, of the troposphere, the PBL, it's directly influenced by processes that happen near the surface, such as the emission of pollution due to human activities. And the PBL has a variability that generally presents a daily cycle. During the night, starting a little after sunset, the PBL presents great stability, having a lower height. During this period, it can be called a stable boundary layer. And during the day, the thickness increases, and it can also be called the convective boundary layer or the mixed layer. And above the stable boundary layer, we can see the residual layer. And so above the PBL, there is the free atmosphere. So a large part of the pollutants and aerosols are trapped in this layer. So there is, we can see an abrupt change in concentration of pollutants between the boundary layer and the free atmosphere above it. And this change can be seen with remote sensing systems such as lidars and ceilometers. The systems that I used in this work were the lidar and ceilometer, and the lidar works like a light radar, emitting laser pulses and measuring the light that returns to the instrument, and it generates profiles of backscattering where we can see huge spikes representing the presence of clouds or aerosols. And when we see an abrupt change of concentration of aerosols, it can be defined as the boundary layer top height. So this is the ceilometer that I used. It has some benefits. It is similar to a lidar, but it has some benefits, such as it's lower cost, it's low maintenance, can operate continuously, but it has some limitations, such as this shorter maximum range and the weaker laser source and noisier signal. These are the photos of the two instruments that I used. The lidar located at IPEM, at the University of São Paulo campus, and the ceilometer is located at Parque Cientec, about 15 kilometers between these locations. The lidar operates at 1064 nanometers, generating second and third harmonics at 532 and 355 nanometers, with a spatial resolution of 7.5. And the data that I use has a temporal resolution of 1 minute. And this is the ceilometer that I use at Parque Cientec. It has an eye-safe laser with a spatial resolution of 15 meters and a temporal resolution of 15 seconds. And the method that I use to obtain the height of the boundary layer is the WCT method, wavelet covariance transfer. It analyzes changes in the step profile, searching for abrupt changes in the concentration of aerosols. So it is defined by the following equation. And it measures the similarity, this function measures similarity between the corrected lidar signal and the HAR function, which represents this step change. And this method is good because it works in many weather situations and is less affected by noise and is easily automated. So here I included a few case studies that I find are very representative of the results we obtained with the WCT method. The first case study is of a clear sky condition, a situation where the PBL is well defined. These two figures show that the intensity of the RCS in function of height and time, and it is possible to see the change in the aerosol concentrations. These profiles are from July 12, and in red I plotted the PBL heights that I obtained with the WCT method. So we can see that in these two cases, the method it was possible to correctly obtain the PBL heights with both the LiDAR and the ceilometer data, and we can clearly see the transition, the daily cycle of the PBL, starting from the stable boundary layer early in the day, and then rising to with the convective layer. Here I just included a picture showing the differences between the results. So the variation was under 200 meters between both instruments. The results were very similar. So in days that are clear sky and that the PBL is well defined, both instruments can be used, and the ceilometer shows very good results compatible with LiDAR results. Here is a second case study with which shows what happens when there is the presence of low clouds near the top of the boundary layer. So we can see that the height of these clouds these clouds cause a lot of attenuation in the signal, and can harm the study of situations of the height of the boundary layer. So we cannot, since it attenuates the signal, we cannot see what's above it, and the method just chooses that as the height of the boundary layer. So in many cases, the presence of clouds really jeopardize the analysis. So, but still, both results were similar. There's a lot more noise with the ceilometer data than the ceilometer data, than the LiDAR data, I mean. But the results are similar. Both show some near close values during the afternoon, showing some more variability in the late afternoon and night. But we see that in days like this, the analysis can be really damaged by the presence of these clouds, so low clouds near the PBL. And this is a third case study that I included an aerosol layer that is multiple aerosol layers, and the method chooses the top layer as the height of the PBL. So we cannot see the rise here going from morning to late afternoon. We can see the lower layer rising, but we cannot see that with the method because it tags the top layer as the height of the boundary layer. So these are some things that I have to consider when I do statistics of, since I have data from almost an entire year, from February to December 2021. I can do statistics such as what is the mean PBL height per hour, but in cases where there's a lot of clouds and a lot of aerosol, these data really causes a lot of variation. It can cause a lot of variation, values that are lower than they should be or higher than they should be due to higher clouds. But still, there we can see I ran the method for the entire period of February to December, and we can see the average height per hour has a daily cycle, and it starts lower with the stable boundary layer, and then the early afternoon, late afternoon starts rising, and we can see the top, the highest values reaching at about 5:30 p.m. UTC, which is 2:30 p.m. local time. So we can see, even though there are many days where the method doesn't accurately find the PBL height, still we can see when we average it that we can see a very clear and well-defined cycle of the PBL with the data from last year with the ceilometer. and I also did a preliminary calculation of the PBL height per month. And in this case, we don't see a lot of variability, and it has a very wide error bars due exactly to what I was saying. There are cases in which the method finds the boundary layer lower than it should be due to low clouds or fog or rain, and there are cases in which it finds higher than it should be due to noise or due to presence of clouds. But we'd see that there is not, from my preliminary results, there's some variation during the year, but it is still very hard to see that due to the presence of these days that there are problematic, that can have they're not clear, that should not be included in the analysis or should be filtered out. So my partial conclusion so far is that in days that are well, the PBL is well defined, or when the presence of clouds is not attenuating the signal too much, the oscillometer found good results, similar results to a LiDAR, even though it is a cheaper instrument and it has a lot of benefits due to not needing maintenance. So we can see that the instrument can be used in days where in many cases in the PBL is well defined, or the presence of clouds isn't too problematic for the analysis. But still, if I want to do an accurate average of these values, I need to filter out these days that are problematic to the analysis. So these are my next steps to check if there's a need to completely remove the profiles with clouds, or if I can still include them, and check if they need to remove adjacent profiles too, and if there are still adjustments that can be made in the numerical method so that the analysis doesn't include these outlier values that could be interfering with the average value, since if this data can be used to study the concentration of CO2 and greenhouse gases, and so these data needs to be as accurate as possible. But still, we can already see the cycle, but from now on, all I need to do is just to improve and filter out these problematic profiles. So these are my preliminary results so far. Thank you.
Thank you, Amanda. Very nice. Now I will open for questions here and from people that are remotely following the presentation. Questions? No?
Maybe just a comment to Amanda. In case to Amanda, you compared the two sites here at USP, and the other one is near, it's at Cientec. So at Cientec, we have the penetration of the sea breeze. So sometimes it's going really to be different, the PBL heights, because PBL heights are more, they are influenced by the local topography and local characteristics. So that's just a comment.
Yes,
but it was really nice to see your results.
Thank you. I could see these and many of the results, the engines of so these differences, and yes, this is something that I should consider when comparing the results from both from different sites. Yes, thank you.
I'd like to make a comment that, as you see, because when you have the sea breeze, it starts say 3, 4 o'clock in the local time. At that time, the PBL is still very well developed, and it goes below the top. So it disturbs, but the top still remains. Of course, if you have a cold front coming, but the sea breeze itself it more or less disrupts the base or in the middle, but not the top. And you can see that from the first results that Amanda showed. And you see the PBL in both places. I'm sorry, the sea breeze penetrating in both places. And the tops was still, when it goes down, then things get messed up. But during the night, during the night, the PBL is doing other stuff.
Questions? No? I have one question for Diogo. Diogo, is it possible, now you are going to have more measurements. Is it possible to follow these days with the contribution from biomass burning or other events?
I think. Yeah, we haven't explored any of that so far, but I think it should be possible. When we look into, at the moment, we're looking into, we're not comparing CO2 data really. I think it should be possible if we, no, yeah, I think it's possible. I think it's totally possible, but we need more days of measurement. But it's something I haven't explored really. But I've seen that in papers where people see the events of stuff like that, fires, and seeing increases in CO2 concentrations above what is expected. So I think it should be possible. Yeah.
Also, I would like to ask Amanda about the comparison between LiDAR and the ceilometer. Some figures that you showed, it's interesting to see that at some it seems to be better the discrimination of the boundary layer with the ceilometer than with the LiDAR. At least with this, that we expect that in the end of the day, it starts decreasing the boundary layer. No?
Yes.
Because when it's the clear sky, both are very, very close. But when you don't have the clear sky, when you have clouds, it seems that the ceilometer represents better. No? Or I'm
yes,
misunderstanding?
It seems to be due to the attenuation of the signal.
Amanda, we cannot hear you.
Oh, you cannot hear me?
Okay, now it's perfect.
Okay. So it seems since the ceilometer has a weaker laser source, the signal gets more attenuated due to this the lower layers. So the intensity of the signal can be very high at these lower layers with the ceilometer. When with the LiDAR, we can still have a very intense signal at the residual layer. So the method, it can end up being good and can help with the analysis, since the method usually searches for these intense signals, intense abrupt changes. So since the signal can attenuate a lot in this lower layer, the method usually finds that as the layer, the top of the boundary layer. And with the ceilometer, with the LiDAR, the signal is still very strong at the residual layer. So sometimes the method can end up tagging the residual layer as the top of the boundary layer instead.
Yeah, okay. It is very nice to have this data because of the modeling. Usually,
I guess that in CNTech, on the same day, there was more cloud on CNTech, probably. No, Amanda? What do you say about that?
There are more clouds. That day that I showed the case study too, yes. There are more clouds and more attenuation of the signal due to the clouds, yes.
Yeah, I think that was the problem, the difference between...
yes, but when we choose a day with clouds, you have clouds here and there, probably, no? You took the data for the LiDAR, bad.
Yeah, there were clouds in both locations, but it varies. Sometimes there are a little bit more clouds showing up in the the signal with the accelerometer data, and sometimes there are more clouds showing up in the lighter location. So on this specific date that I show, there are a bit more clouds in the Praxi intact location.
On that example in particular.
Yeah, but
Yes.
but when she compared both, to put both figures, it seems more well, at least
Noisy.
theory. Yeah, you know. And then when she made the convolution of the boundary layer, it seems more that it's close to what we expected because it starts decreasing.
Yes.
And the LiDAR no.
Yeah, that's right.
It's because of this that I was asking.
Mm-hmm.
Okay. Well, I don't know if we have more questions. Do you have more questions here? No? People like to ask something? Well, if not, then I would like to thank all the presenters. It was really nice to know because even us that we are working in the project, we are not aware of all the details and data and measurements that are being performed. It was quite good to have all these results. Thank you very much. Thank you for, and also for the attention for people that are here and remotely following the presentations. Thank you.
Pode falar português agora?
Interrompe a transmissão?